Welcome to um, programming languages for civil engineering students. In this video, I will discuss how we can use the TCL programming language to for the dynamic analysis of one story moment frame with viscous dampers. Okay, this is the schematic diagram of the model, that is a single bay frame with the height 3 meters and the length of the bay is 5 meters, and have some the stiffness of this damper KD, and the damping coefficient, that is CD of the damper, is somewhat some value. Let us say the value is they fix the value as CD is equal to 20.74 kilonewton second per meter whole power 0.35. The exponent A is equal to 0.35, and then axial stiffness, that is the stiffness of that damper, is 25 kilonewton mm. In this, all units are in mm and kilonewton. Okay, and it is carrying a weight of 1000 kilonewton. Okay, let us open first. This is the simple coding in TCL. Okay, this is the TCL format. This is YPAL and model base builder. This is NDM, that is what you call 2D, and this for each node there is 3 degree of freedom. Okay, and create a data directory. You have to set output, then you have to set the length of that bay, and you have to set the height of that bay, that is 3000 mm. Length of that bay is 5000 mm. We have to define the nodal coordinates: node 1 0 0, and node 2, that is the node 2 L and 0 in x and y direction, and not node 3 0, but height is h. So in this way we can give the nodal coordinates. We have to define the nodal coordinates. Then after single point constraint boundary conditions, we have to fix that this is the node 1 in x direction, y direction, z direction is fixed because it is fixed support. So in this way we can define the fixed constraints, supports. Then so in this way you have to set the mass. Okay, you have to convert kilonewton to kg. Then assign values. We have to assign for that particular nodes 3 and 4th node, that is half of that load, and we have to set the time period of a natural frequency, natural period, from calculating any standard formulas. Then you have to give the properties of columns and beams. You have to set that is stiffness and E, and moment of inertia of column, moment of inertia of the beam, and area of that and damper properties. We have to give the damper properties KD and whatever it may be. And uniaxial, we have to define the viscous damper material, uniaxial material, viscous damper 1, and we have to define that values KD, CD, and that power. Okay, and define geometric transformation, that linear, and define elements. We have to define the elements. Element elastic, it is first node. That first node is connected with the columns, that 1 3 node. This is the first column, and an element elastic beam column, that is second column, we connected to second node and 4th node. So we have to give that area, that elasticity, Young's modulus, and moment, that moment of inertia for that column. Okay, and for beam also have to give the same point. There is only one beam, that is we have to give the tag name, that 3 and 3 and 4, it's connected between 3 and 4 the nodes. So in this way we have to give that area of that beam, and so on, so and so. Then damper, we have to give the damper properties. We are connecting of node, that is first node and fourth node we are connecting, so we have to give that direction, only one direction, and puts model and time series, and define we have to give that file name, in earthquake file name. So then after define, we have to define the recorders. We have what are the output is recorded in our recorders. There in this 3 and 4th nodes are recorded, the displacement and output, the acceleration out at node 4, whatever it may be. Then at the base, what is the base response, also we will get, and damper response, damper force, damper displacement is also we can get. Then we have to set first eigen mode, we have to set the eigen values here. Then we have to define the pattern. Then we have to create the analysis, wipe analysis constraint, and we have to integer, integrator, new mark. You have to define the new mark parameters. Then analysis transient and analysis for number of steps, that is 4096 steps, that is into 10 of interval 0.01. Then you close. Okay, you save this. Okay, then after you have to download this from OpenSys. You just type source, and suppose I want, you have to give the name, of this here, source, paste, and .tcl. okay, you have to click .tcl, you have to add TCL. Then after you will get a diagram like this. In this you can see the frame is moving to and fro. You can see here, this is the shape of the frame with the viscous damper. You can see here the damper, and this is the displacement of response. I mean how how the moment, single moment frame is responding. So in this way you can run the program in this OpenSys. Then if you want to see the values, you can see in this same folder you can see output. The output is, you can see here, the displacement. You can see here, this is the time, this is the displacement at third node, and this is the displacement at fourth node. This is the time history response. You can get the time history response here. So in this way you can easily find the response of the structure in this OpenSys. Okay, so here you can see damping force also you can get, and what is the damping force, and you can get the damping displacement. You can get the damping displacement, and you can get n base. And so in this way, frame force, what is the force of the frame, you can get this also. So in this way you can run the program. If you want to plot this, you can use any of the programming languages like FreeMat, Scilab, MATLAB, and GNU-Octave, or you can use Excel, or you can use GNU-Plot also. According to your suitability you can use. Okay, in this way we can simply modify the existing file, and you can create a model. Thank you for watching this video.